Good morning, everyone. This is Joe Consorte, your reporter for today. My topic is all about floating point and number formats. In computing, an arithmetic logic unit, or the ALU, is a digital circuit that performs arithmetic and logical operations. The ALU is a fundamental building block of the central processing unit of a computer, and even the simplest microprocessors contain one purpose, such as maintaining timers. ALU is a necessity for a computer because it is guaranteed that a computer will have to compute basic mathematical operations, including addition, subtraction, multiplication, and division. So what is a floating point number format? Just a simple question. Any number which has a point in it is called a floating point. No, not every point is a floating point. Okay, for example, 89.1, 291.0, 0.23, 3.56. Okay. Do you think that it is a floating point number? How about 1.2, 2.3, 3.4, 4.5? Okay. The first set of examples are called floating point numbers, and the second set of examples are called fixed point number. Okay. So what is the difference between the two? The first set of example is a floating point number, which means any number where the position of the point is not fixed. Okay. And the second set of examples are called fixed point number. The position of the point is fixed. When the CPU executes a program that is calling for a floating point operation, there are three ways by which it can carry out the operation. Firstly, it may call a floating point until emulator, which is a floating point library, using a series of simple fixed point arithmetic operations which can run on an integer ALU. The emulators can save the added hardware cost of a FPU but are significantly slow. Secondly, it may use an add-on FPUs that are entirely separate from the CPU and are typically sold as an optional add-ons which are purchased only when they are needed to speed up math-intensive operations. IEEE 754 standard. IEEE 754 standard is a technical standard established by IEEE and the most widely used standard for floating point computation, followed by many hardware, CPU and FPU, and software implementation. IEEE 754 standard specifies a single precision number as having sign bit which is of 1 bit length, an exponent of with 8 bits, and a significant precision of 24 bits out of 23 bits are explicitly stored and 1 bit is implicit 1. IEEE 754 also defines certain format which are a set of representation of numerical values and symbols. It may also include how the sets are encoded. Floating point number, a real number, and it is used in computer when the number is outside the integer range of the computer, it is too large or too small, and contains a decimal fraction. In the decimal system, a decimal point or the radix point separates the whole numbers from the fractional part. For example, 37.25, the whole number is 37 and the fraction is 25. 123.567, the whole number is 123 and the fraction is 567. In binary equivalent, of a floating point number can be computed by computing the binary representation of each part. In whole number, we can use subtraction or division. And in fractional part, we can use subtraction and multiplication. In the binary representation of a floating point number, the column values will be as follows. For example, we need to convert 37.25 in its floating point number. First, we need to convert 0.25 using multiplication method. First, we need to multiply fraction by 2 until it becomes 0. 0.25 times 2 equals 0.25 times 2, 1.0. Then, we need to collect the whole parts and place them after the radix point. In collecting the whole parts, we need to start from 0.25 down to 1.01. Another method, we can convert the 0.25 using the subtraction method. First, we need to write the positional powers of 2 and column values for the fractional part. Next, start subtracting the column values from left to right. Place a 0 if the value cannot be subtracted, or 1 if it can, until fraction becomes 0. 0.25 minus 0.25 equals 0.0. We need to place 0 to 0.5 because it cannot be subtracted, and we need to put 1 on 0.25 since 0.25 can be subtracted by number 0.25. So the answer is 0.01. Binary equivalent of floating point number. Given 37.25, we need to convert the 37 in 0.25 using the subtraction method. Okay, first, we need to write the powers of 2 and column values of the fractional part. Start subtracting the column values from left to right. Place a 0 if the value cannot be subtracted, or 1 if can until the fraction becomes 0. Okay, 37.25, the value is 100,101.01. Given the following binary representation, 37.25 equals 100,101.01, how we can represent the whole and fraction part of the binary representation in 4 bytes. The solution is normalization. Normalization is shifting of numbers left by increasing the exponent until leading zeros eliminated. Converting decimal numbers into a standard format. Normalization provides number with exponent 0 if not specified. It increase and decrease exponent to shift decimal point to proper position. It also decrease exponent to eliminate leading zeros on mantissa. It also correct precision by adding zeros or discarding and rounding less significant digits. Every binary number except the one corresponding on the zero can be normalized by choosing the exponent so that the radix point falls to the right of the leftmost 1 bit. Okay, in 37.25 equals 100,101.01, we need to move the radix point 5 times. So the radix point is near on the first bit 1. So the answer, when we normalize the 37.25, The answer is 1.00100101. After normalizing, the numbers now have different mantissa and exponent. IEEE floating point representation. The floating point numbers can be represented by binary codes by dividing them into three parts: the sign, the exponent, and the mantissa. The first or leftmost field where floating point representation will be the sign bit, 0 for the positive number and 1 for the negative number. The second field of the floating point number will be the exponent. Since we must be able to represent both positive and negative exponent, we will use a convention which uses a value known as a bias of 127 to determine the representation of the exponent. The bias exponent, the value actually stored, will range from 0 through 225. This is the range of values that can be represented by 8-bit unsigned binary numbers. The mantissa is the set of zeros and ones to the left of the radix point of the normalized binary number. The mantissa is stored in a 23-bit field. Now, we are going to find the IEEE floating point representation of 40.15625. Step 1. Compute the binary equivalent of the whole part and the fractional part. Convert 40 and 0.15625 to their binary equivalent. So, the answer for 40.15625 is equals to 101,000.00101. Step 2. Normalize the number by moving the decimal point to the right of the leftmost one. 101,000.00101 equals 1.0100000101. Step 3. Convert the exponent to the bias exponent. 127 plus 5 equals 132. 132 is equals to 1,000,000,100. To find the bias exponent, we need to divide 132 by 2 until the quotient becomes 0. We are going to get the exponents upward. So 132 is equals to 1,000,000,100. Step 4. Store the result from above. Sign, since our problem is positive, the sign is 0, and we get the exponent from step 3, and we are going to get the mantissa from step 4. So the result, sign equals 0, exponent is 1,000,000,100, and the mantissa is 0,1,000,00101. Okay, the first problem, we have the positive value. Now we are going to convert decimal floating point values to store in IEEE standard values with negative sign. Find the IEEE floating point representation of negative 24.75. First, we are going to compute the binary equivalent of the whole part and the fractional part. Next, we are going to normalize by moving the decimal point of the right to the leftmost one. Next, we are going to convert the exponent to the bias exponent. And then, we are going to store the results from since our problem is negative, our sign bit is 1, and we are going to get the exponent on the step 3, and for the mantissa, we are going to get it from step 2. And that's it. We're done in floating point number format. I hope this video will help you in converting decimal floating point to IEEE floating point standard. Later, I will give you a short quiz for you to apply the floating point number format. Bye-bye!